So I'm going to show you how to download a non-HTML5 PhET simulation. So we're going to be doing, this is one that you can play with today, and we'll be downloading another one for lab on Wednesday that you'll need to be able to do this. So here's how you do it. Now it's different for a Mac and for a PC. Mac's a little bit harder because Mac really doesn't like Java. PCs are a little bit more okay with it, and so it's a little tricky. So we're going to go through this, and I'll show you the steps. So the first thing we're going to do is we're going to hit download, and it's going to, I already have it downloaded, but we'll do it in here. So it's going to download it as a Java archive, and so I'm going to hit save. Okay. Now if you just click on it right here, I'll show you what not to do. If you click on this, it's going to say you have Java, there's security preferences, blah, blah, blah. So what you got to do is you got to go back, and now it actually won't show it here. You're going to need to go to your Finder. You need to go back to where it was, and you need to go to the right file, which is over here, and you need to so here it is. So I have two files, but I'm going to show you the one that I haven't done yet. And so this is a jar file, a Java file. So I'm going to double click on it and see what happens. And now it says you still can't do it. I'm going to double click on it again, and it says you still can't do it. Okay, so now I'm going to right click on it. So right click, open with, and then I'm going to go Java Launcher. And when you do that, behold, there is an open button. This is the whole part, is you have to go to file, you have to right click and open it, and then when you open with the Java file that I just showed, then you hit open, and then it says okay, now you can open it. So you can't open these files, it just takes a sec. So practice that with this. So here we go. So what this is this is showing us, it's a really cool simulation that shows all the variables. So this is the energy plot that we were dealing with, where this is our reactants energy, and this is our products energy, okay? And in between here is our activation energy, or sorry, our energy barrier, which we'll show is a combination of our the difference in energy of reactant products. So if we do the example of the N2 and O2, we saw that the reactants had a lower energy than the products, and so we have a higher energy barrier. Now, this is the energy, so the difference between the energy here and here, so this difference right here, this is called enthalpy, or delta H. That tells you straight up the energy difference between the reactants and products, but it doesn't tell you all the information. This extra bit, this from this little hump here, this is showing you how hard it is to go between reactants and products, or how unstable this intermediate you make to get to your products. And so this can change, and so I can change what this is. So for, if this would be like very little activation energy, where this would be much greater activation energy. And so this will make a big difference on if a reaction is spontaneous at room temperature. And so that's, so again, the first things we'll look at are just the energy barriers. And so we'll start off with what we had with N2 and O2, and we'll go from there. So we have another thing where we can increase the temperature of our surface. And so what we're going to do is I'm going to add some molecules to the chamber. So I'm going to put, we'll do like 50 A's, no B's. Now you'll notice that this is showing you the kinetic energy as a function of the speed at which they're bouncing around. And so we can see that there's not, so every once in a while you might get something that looks like it escapes, but overall at this temperature that we have around 160 Kelvin, which is actually pretty cold, it's way below zero, that there is just no way that we're making any B. It's just not going to happen. So this is showing you that this reaction would not happen, or would not occur. And so there's two ways, and if we have a given chemical reaction, I can't change this ruler without adding something like a catalyst. And so the only way I can do it is by adding or increasing the temperature. And so this is why reactions happen at faster temperatures, is that if I increase the temperature, we can see if we can get this up to above freezing. So 298 degrees is room temperature. And so it's a little above room temperature, but now we can see that more of these balls are getting closer to getting up and over this energy barrier, but still you can see that we haven't created 1B yet, okay? And so this high energy barrier makes a big difference on how likely reaction is to occur. So let's get this going. Let's get the temperature way up. So let's try to go as high as we can go and see, like, if we can force just by increasing the temperature of the reaction, how much B we can make. So we are going up and up and up and up all the way to the top. Okay, and so now we can see that, oh, there's our first B. So we can start getting these molecules. But notice that once you've made a B molecule, we just got one going back. So we can see the averages. We only have 2 or 4% of the molecules are B. And you can see just how hard it is to overcome the energy barrier, even when you have enough energy. Okay, so this is a really nice visualization of both how A can be reacted to form B, but also that this is reversible, meaning that you can always go from products back to reactants. And actually you can see, because the energy of the products is so much, so see how this is so much higher, it's much easier. This gap is a much lower wall to get over, and so B is more likely, the rate will be faster going back. So if you follow a B molecule, an individual B molecule more likely to go back to A than if you follow an A molecule here and go to B. Now we're kind of setting up at 40 and 10, and at some point we're going to reach what we call chemical equilibrium, which is that even though we're going back and forth between these two reactants and products, we're going to have a ratio of A to B that's constant. So that's what we call chemical equilibrium. Now, so we've established that for this particular energy barrier, we are going to favor staying as A and not to B. So increasing the temperature did increase the amount of B molecules by a good amount, but it does not do enough to make all of the A to go to B. And in this case, it's very hard to. Okay, so let's add a catalyst. A catalyst, what a catalyst can do is it can change the energy barrier. So let's say we have a catalyst and see for the same temperature how likely it is. Now you can see when I've done this, because this energy difference, it's still these B molecules are just kind of going right back to A. And so we can see that if we follow our molecules in chamber, that adding a catalyst in this case does increase the rate at which we make B, but it also increases the rate at which you go from B to A. So you can see that we're still at this 40 to 10 ratio. Okay, so that's all you can do for a chemical reaction. You can't change the energies that the reactants have, and you can't change the energies that the products have. Those are just set in stone for a given chemical reactant or chemical product. Okay, and so if I decrease some of the temperature, we might see that once we get enough of these molecules over to B, that they might stay there. But I don't think it's going to matter that much. Okay, so you can keep playing with this. You can let it sit here, go have some food, come back, and you can see that how these ratios set up, but it's staying pretty constant. Okay, so that's the first thing that you can change in a chemical reaction is the activation. So we have two things we talked about. First, we can add thermal energy, we can remove thermal energy. So adding thermal energy can make your chemical reaction go faster. Remove it can go slower, and that's actually why we refrigerate our food. If we want to keep chemical reactions from happening, so food spoilage, we're going to put it in the refrigerator. And if we really want to slow it down, we can put it in the freezer. That's just the simple thermodynamics of slowing the rates of chemical reaction. In this case, the chemical reactions associated with food spoilage. Okay, so those are the two things that we can do for chemical reaction. But I just want to point out that if I can change my chemical reaction, so now this is a different chemical reaction, let's do a couple things. What if we make the energy barrier high for both A and B? Okay. And now you can see that once you're B, it's going to be more likely, and we'll add a little bit of thermal energy to kind of get more over there. You can see you're more likely to get the molecules to stay at B. So now you can see that our A is gone down into the 35, 34. The B's are kind of bouncing back when they head over. And so we're getting a much kind of more even ratio. It's not quite half and half. And if I were to make these exactly the same, then over time we should expect that just statistically we should have an even distribution of A and B. Okay, and so that is it's pretty unlikely, but you can just kind of see how the activation energy barrier works. And again, if we make this 0, then really it's just random. We should really expect to see a 50-50 mix between A and B. Again, this is not very likely, but we should expect 25 and 25 settling up pretty quickly because it's just a random distribution of molecules moving around. So the other one we looked at, so first we looked at the energy of, let's see, so this is what we looked at first, the energy of the products being higher than the reactants. We saw that it was hard. It was hard to make products. Well, let's make it easier. So let's now switch it up. Let's make the product energy really low, the reactant energy really high, and let's make this activation energy low. You can see the barrier gets lower the higher the energy of the reactant. So higher energy reactants means that you have you're less stable and you're more likely to react. And so now we can see that we are really favoring the B side, and it's almost a reversal of what we saw the other way because we basically have switched the energies here. So now this energy barrier is much bigger. So once you go to the B side, it's much harder to get back. Once you're to the A side, it's much easier to get here. So we can see that this is almost a flip-flop, and I've done it to be if I make basically 0 activation energy, it doesn't mean that you'll never have an A. You always have some B molecules, at least at this temperature. Now, if we decrease the temperature a little bit, we might be able to make it so that once you're in B, you can never get to A. So let's do that. So let's bring it way down. And in this case, we basically make a thermal trap where once you have, once the last one goes over, and once you're over, then you can never go back. It's like Hotel California, but with chemistry, because you're just once the energy barrier is too high. And so this is sometimes how we can, in chemistry, if I really want this product B, and it's in this way, oh, we got A, now it's back. Then we can basically cool this reaction down to trap the product that we actually want and force the reaction to go in this direction. So again, we still see at this temperature that there is the chance that a B can go back to A, but it's very small. So it's all probability into how many. But the point here is that even this is strongly favoring B, you can always have some A being formed. It's reversible, but it's definitely favoring for B when I have this. And if the other thing you can do is if you want to have a distribution, it may take a lot longer to reach thermal equilibrium, but if we have this, we still should get a 50-50 distribution, whereas it's very unlikely to go back and forth, but eventually, if enough molecules have enough time to make it over, it might take a long time, then we should have some distribution here. So anyway, you can play with this. Definitely check it out. They have a couple other things that are a little bit more. So you could say, you could look here and say number of gas molecules, and you can look at their average speed and see that they're about the same. You can also look at the energy histogram, and this shows you the kinetic energies as a function of, move this into the screen over here. So you can look at the speed which is associated with temperature. So if we increase the temperature, we can see an increase in the distribution of speeds. They should be moving more to the right and flattening out a little bit. And kinetic energy as well should see this kind of distribution of higher molecules have all the distributions. And we're going to actually, we've drawn this plot of kinetic energy versus number of particles. And so this is actually just kind of replicating. We're going to do this, but you can see how it can change. Anyway, this is a nice little visualization. Let's see. I'm not sure if there's any other information here. No? Okay. Of how, so just to summarize, the energy of reactants and products, you can either have reactions where the reactants have a higher energy than the products. Those tend to favor the formation of products because this barrier is a lot smaller. You can have reactions in which the products have a higher energy than the reactants. Still can happen, but you're more likely to stay a product, or a reactant, I mean, because the barrier is smaller this way. And if you have a chemical reaction with a high activation energy, you can add something like an enzyme and bring this down, which would allow It makes it both easier to make reactants and products, but in this case, you would have more products being formed because the energy barrier is smaller in this way. So nice little simulation to show you two graphs, both the energy graph that we've drawn as well as thinking about temperature and speeds of molecules in a more concrete way.